Hi, in this video we're going to take a look at the contradiction rules in the Fitch style system. These rules don't actually correspond to any of the logical connectives that we've seen so far. Nevertheless, they play a very important role in Fitch style system. So let's take a look at them. Alright, so before we take a look at the contradiction rules in the Fitch style system, I want to talk about the relationship between validity and inconsistency. So first, let's recall what a valid argument is. One textbook definition states it in the following way. If the premises are true, then the conclusion must be true. So if an argument has that property, the property is such that whenever all of its premises are true, there's no way for the conclusion to be false, then it's a valid argument. But another way of understanding it, and this really is just saying the same thing, is this. It is not possible, or it is impossible, for the premises to be true and the conclusion false. So if an argument has the property such that it's impossible for all of its premises to be true and its conclusion false, then that is going to be a valid argument. Now, notice that if an argument has inconsistent premises, then that means at least one of the premises has to be false always. There's no way in which you can make all the premises true. And if there's no way in which you can make all the premises true, it turns out that it is impossible for all the premises to be true and the conclusion false. So, surprisingly, if you have inconsistent premises in an argument, then it is, by the definition of validity, a valid argument. Now, one of the things that follows from the fact that any argument that has inconsistent premises is a valid argument is that the inference to the conclusion is always a good inference. It's always a valid inference. And that strikes students first coming to logic as being very strange, right? You should be saying to yourself, why would that be a valid inference to any particular conclusion if the premises are inconsistent? So here's another way to think about it instead of just satisfying the definition of validity. Let's suppose that we had inconsistent premises, yet all of our premises were in fact true. What that would entail is that contradictions actually happen in the world in which we find ourselves. That is, the world in which we find ourselves, it could be a particular way and not that particular way. And if that hurts your head, good, it should, because it doesn't make any sense. But on the assumption that inconsistent premises can all be true, that would follow as a result. The world could be a way and not that very way at the same place, the same time, the same whatever sort of dimensions we need to take into account. And we'll let quantum physicists or whoever figure that out for us. Now, why would that be the case? Well, if something can be both true and false at the same time, then just because I've discovered that something is true, that does not preclude that it's false. And just because I've discovered that something is false, that does not preclude the possibility that it's true. And as a result, anything follows from inconsistent premises that are all true. Anything. Whatever, anything goes in such a world in which there can be contradictions. Nothing gets precluded. And so that's why you can conclude anything from a set of inconsistent premises. Okay, so those are two ways to think about why we have a legitimate inference from inconsistent premises to a conclusion. And again, you might think that that's really strange, but you can be comforted, right? So, oh well, if we have inconsistent premises and we get to infer anything from such a set of premises, it'll turn out that the argument is never sound. So even though it's a valid argument, because one of those premises does have to be false, by what we mean by inconsistent premises, it can never be a sound argument. So such arguments are always bad, even though the inference is good. It's just that the badness of those types of arguments is that we're guaranteed that one of the premises is false, that the world is not like that. All right, now that we've taken a look at the relationship between validity and inconsistency, let's take a look at the contradiction rules in Fitch, how they work in Fitch style system. Okay, so the first rule that we're going to take a look at is contradiction introduction. And informally, we just know that to assert P, which is to say that P is true, whatever proposition that is, whatever statement it is, and to say not P is to say that P is false. So if I say both of those, P and not P, I'm saying it's true and I'm saying that it's false at the same time in the same place. I'm saying that the world is a particular way and that it's not that way at the same time, same place, etc. And that means they're inconsistent. Only one of those can be true. So putting that formally, we get to introduce this turnstile symbol, which is the symbol for contradiction. So that's the turnstile symbol, symbol often used for to represent that a contradiction has been achieved. So we can introduce, if we have established an explicit contradiction P and not P, whatever propositions P is. So P might be an atomic proposition, it might be a complex proposition, but if you say that the proposition is true and to say not the case P just is to say then that it's false, then we have got an inconsistency and therefore we have got a contradiction. So what our diagram represents here is that at some point we have a proposition P, and then at some point in our proof we have the proposition not P. It doesn't matter whether this comes before and this comes after. It just matters that we have gotten those. We get to accept both of those as being true, and they can't both be true. But if we have those, then by the rule contradiction introduction, we can then infer a contradiction. That's the symbol telling us that we have an inference. We can infer a contradiction, and then we have to point to whoever is reading our proof that it's these two propositions that are generating that contradiction. All right, so here we have a pretty simple application of the contradiction introduction rule. We see in the proof here that we have our Fitch bar telling us that the propositions above it are our premises and that we get to accept them to be true. The problem is we see that means in step 1 we're being told that it's true that A is a cube, but in step 2 we're told that it's not the case that A is a cube, that it's false that A is a cube. Well, which is it? Is it true or is it false? It can't be both, which is why we get to infer then a contradiction. So we do that by applying the contradiction introduction rule, and for whoever's reading the proof, we have to point them to the propositions that are in fact inconsistent with one another, that are generating that contradiction. All right, so at the end of the video, we'll take a look at how the contradiction introduction works in the Fitch computer program. All right, so there's another way in which propositions can be inconsistent with one another, or even for a proposition to be self-contradictory. And that has to do with the meaning of the predicates instead of relying on the assertion of a proposition and its negation. So, for instance, if I say that John is a bachelor and John is married, that's going to be inconsistent or contradictory because being a bachelor precludes being married and being married precludes being a bachelor by the meaning of those words. Likewise, if I assert the proposition there are married bachelors, that's going to be self-contradictory. Now, Fitch can't handle all predicates. It would be very difficult, if not impossible, physically impossible feat to program all of the possible contradictions between all the possible English predicates. Nevertheless, Anacon is sensitive to the meaning of the block language predicates, except for the adjoins and between predicate. So Anacon, outside of adjoins and between, can detect when propositions are inconsistent or even self-contradictory, as long as it's with the block languages. So what that means then in Fitch system, if we have a set of propositions that are Tarski world impossible, then we can use Anacon to introduce the contradiction symbol. So for instance, it's Tarski's world impossible for A to be a cube and a dodecahedron. It can only be one shape at a time in Tarski's world. So as a result of that, we can use Anacon to introduce a contradiction symbol, and we have to point to the propositions that are Tarski's world impossible, that they can't both be true at the same time in Tarski's world. And again, we'll have a chance to take a look at how this works in the Fitch computer program. All right, so let's turn our attention now to the contradiction elimination rule in the Fitch style system. So going back to what I was saying at the beginning of this lecture video, if we have a set of inconsistent propositions, that always satisfies our definition of validity. It'll always be the case that it's impossible for all of those propositions to be true and the inference from those propositions to be false. And that's because it'll always be the case that at least one of those propositions is false. So whatever the inference is, that will always be a valid inference to that proposition. The other way that we talked about it, to think about it, is if it really turns out that contradictions happen in the world, anything goes, because if something is the case, it could also be not the case. So you can never preclude anything from being the case. Therefore, you can infer anything. Okay, so formally speaking, if we are able to prove a contradiction, whether that's from having P and not the case P, and thereby using the contradiction introduction rule to get it, or whether that's by using Anacon because of the inconsistency of the block language predicates. As long as we're able to prove that in a proof in the Fitch system, then we can assert anything. So in this example, what this diagram is telling us is if you get to accept a contradiction, you find an inconsistency, then you can infer whatever proposition. It doesn't matter what proposition it is, you get to infer it. And the way that we cite that is we apply the contradiction elimination rule, and we cite the contradiction that was generated. And here we have an example in which we used Anacon, in which Anacon was used. So again, we have A is a cube, and it's being asserted that A is a dodecahedron, but A in Tarski's world cannot be both a cube and a dodecahedron. That is an impossibility in Tarski's world. So we get a contradiction by applying the Anacon mechanism to the propositions that are inconsistent with one another by the meaning of their predicates. So then notice that what I infer as a result from contradiction elimination, citing step 3 because that's where we have the contradiction symbol, I infer that A is between B and C. And notice that the between relation has nothing to do with cubeness and has nothing to do with dodecahedronness. And the reason why I did that is to try to highlight the point that anything at all follows from a contradiction. I could have inferred that the sun is cold. I could have inferred all sorts of things, right? But here I inferred that A is between B and C. All right, so we'll also get to take a look about how this works in the Fitch computer program. So let's turn to doing that. All right, we're going to take a look at how we can apply the contradiction introduction rule in the Fitch computer program. So here we have our Fitch bar, and we have two propositions above the Fitch bar, so those are our premises. Our first premise says that A is to the right of B, and our second premise says that it's not the case that A is to the right of B. That means this is asserting A is to the right of B is true, where this is asserting that A is to the right of B is false. So they're inconsistent. They take the form P and not the case P. So that means, since they're inconsistent, they take that form, P and not P. I can come to introduction and find the turnstile, which is our contradiction sign. I have to cite the propositions that are contradictory with one another, and then put in the contradiction sign. So that's a pretty easy case. But what I want you to also know is that even complex propositions can take the form P and not the case P. So if they have the proposition both A is to the right of B and A is a cube, and then not the case A is to the right of B and A is a cube, that still takes the form of P and not P, because this is asserting that conjunction to be true, but here we're asserting the very same conjunction that's in 1 to be false, since our negation sign is being negated with the parentheses surrounding the conjunction in question. So since that takes the form P and not P, we can use the contradiction introduction rule to introduce the contradiction symbol. Again, we have to cite the propositions that are contradictory with one another, and we see that we can introduce the sign. Okay, so there's yet another way in which we can introduce the contradiction symbol, but it's not by way of the contradiction introduction rule. Instead, it's through the anicon mechanism. So, for instance, let's say that we still have A is to the right of B, but then we are told that A is in the same column as B. Well, if you think about it, in Tarski's world, if A is in the same column as B, then it's neither to the right, then A is neither to the right of B, nor is A to the left of B. So, premise 1 cannot be true at the same time that premise 2 is true, and vice versa. But notice that it doesn't take the form P and not P. As a result, we cannot use the contradiction introduction rule. We would have to instead use anicon. We cite the two propositions that are contradictory with one another. And since it's not the adjoins predicate and it's not the between predicate, Anacon will be able to determine that those two propositions are inconsistent or contradictory. All right, now let's turn our attention to how we applied the contradiction elimination rule. All right, so in order to apply the contradiction elimination rule, we need to have discovered an inconsistency in our proof. That is, we need to have the contradiction symbol somewhere in our proof. So in this case, we have our two premises, and our first premise says that if A is medium, then A is the same size as B. And in our second premise, we're saying of the very same proposition that it's false, that it's not the case that. So of course that takes the form P and not P, which is the form that allows us to apply contradiction introduction. And that's how we're going to get our contradiction symbol. So we apply contradiction introduction to premises 1 and 2. And now we have our contradiction symbol. Because we have our contradiction symbol, now I can infer anything, because anything follows from a contradiction. If contradictions can actually happen, anything goes whatsoever. If you've discovered an inconsistency, an inference from those inconsistent propositions will be a valid inference, because the premises of the leading to the inference cannot all be true, satisfying the definition of validity that it's impossible for all the premises to be true and the conclusion be false. All right, so since we can infer anything, let's infer something that's even outside of the block language. A is happy. We cite the contradiction symbol. We come to elimination and find the contradiction symbol for contradiction elimination, and we see that it does in fact follow. So I could put anything as an inference. We could do F is a dodecahedron, which is clearly has nothing to do with our first two premises. And we will see that it follows. I could put A and we see that it follows. We can do adjoins. And we see that it follows. All right, that wraps up this video on the contradiction rules. I hope you found them useful.